All right, the two problems I'm going to talk about are, first, how complex should a model be? So if we're going to build an individual-based model, what should be in it? The second problem is how do we model individual behavior? So the most important thing about an individual-based model is that we model the behavior of the individuals, so how do we do that? And the strategy for making those decisions that I'm talking about is called pattern-oriented modeling. I'll present two examples, one having to do with a model of a coffee farm in which birds and beetles are important, and the second example has to do with managing water projects and dams for fish populations. And then at the end, I'll talk about individual-based modeling and more larger scale issues such as how do you integrate ecological levels of organization, management versus theoretical ecology, and then if there's time I'll say a few words about what doing individual-based modeling means to those who also do field science. I need to start by acknowledging some of the people that I've worked with and without whom I wouldn't be able to stand here and sound the least bit intelligent. First is Volker Grimm, my friend at the UFZ Helmholtz Center in Germany, and I've learned a lot about modeling and the philosophy of modeling from Volker. And then the ecologist that I work with most closely is Brett Harvey, who's with the U.S. Forest Service, also in our town of Arcata, California. Also, we've had the good fortune to have some very good computer programmers work with us and help develop the software for our models. And most recently, most of our modeling work has been done using the NetLogo software. So to talk about why individual-based models are important, I'm going to start by talking about simple models in contrast to individual-based models, which most people think of as complex models. Simple models have been extremely popular in ecology for ever since ecology really started as a modeling practice. Some key advantages of simple models are they're easy to understand. It's easy to analyze a model and figure out exactly what it's doing, how it behaves. For models that are that most of the knowledge in the model is from calibrating the model to data, it's easier and less uncertain to calibrate a simple model if there's only a limited amount of data. And these models are more appealing to mathematicians because they're written in the common language of equations, and so they're very easy to communicate, they're easy to analyze it. Mathematicians know what to do with a simple set of equations. So one of the most common simple models is this population model. Probably some of you are familiar with this. It's just a model of how the population of some group of animals, for example, this is widely used in ocean fish management. So it just says that the population at the next time step is equal to the population at the current time step times this simple function of the current population, a growth rate parameter, and a carrying capacity parameter. And if you vary this growth rate, you get a population that very slowly approaches the carrying capacity, or very rapidly approaches the carrying capacity, or even can go past the carrying capacity and oscillate back and forth. But these kinds of models have important limitations. They're not useful when behavior of the individuals is important. So these kind of models might be very good if animals or plants were just like atoms and followed simple rules of physics, but instead they have behavior. They make decisions in response to their conditions. Simple models aren't useful when the differences among the individuals are important. For example, if their size makes a difference or where they are in their life cycle. And these models tend not to be as useful when habitat effects or environmental effects are important. Or as Volker Grimm says, when you realize that what you want to understand is not the model itself, but you want to understand reality. So simple models are easy, make it easy to understand the model, but they don't always help us understand reality. So for example, with this simple population model, what if the question you were trying to answer is, what are the effects of having fewer fish that are age 8 and more that are age 3? Well, you can't answer that question because the age of the fish is not in this model. And similarly, if the question is, what are the effects of climate change? You can't answer that question with this model because there are no effects of the environment except through this carrying capacity parameter. So the lesson is that complex problems, like the ones that most of us face in the real world, require complex models. So in real ecological systems, things like individual behavior, variability among the individuals, and environmental effects are extremely important. And I think ecology has changed, and even the theoretical ecologists know this now, and they're realizing that they have to work with more complex models than they have in the past. And so individual-based models are natural for these kinds of problems because they deal with what happens to the individual. So it's easy to put in models of behavior. It's easy to represent the variability among the individuals. And very often the effects of the environment are much easier to understand and to represent at the individual level than at the population level. So what is an individual-based model? Well, it's simply a simulation model of an ecological system in which the population characteristics, and remember that that's what we're ultimately interested in, is the population characteristics, such as the number of individuals, how long the population might last before going extinct, etc., where those characteristics emerge from what happens to simulated individuals. And often what we have to include about these individuals includes something about their physiology, their behavior, and how they interact with each other and with their environment. So this model then represents the simulated individuals inside a virtual environment in the computer. So why do we use these individual-based models? First, we use them not only to address problems that are too complex for simpler equation-based models, but also when for problems that are too complicated to answer just with field studies. If some of you probably have a lot of experience with field research, and you realize that when you go out and design a field experiment, there are only so many things you can control and vary. There's only so much you can learn from a field experiment, and modeling can be a way to take what you've learned in a limited set of field experiments and try to extend it to conditions that you weren't able to observe in the field. Second reason to use individual-based models is because the effects of things like habitat or biological interactions like competition with a new species or food, changes in food supply are easier to represent and, of course, to understand the effects of behavior. And these individual-based models are really one of the few ways we have to try to integrate across ecological levels. The whole purpose is to understand how population ecology is affected by the individuals, but at the same time how the individuals are affected by the state of the population. Of course, these complex models have disadvantages too. When a model is more complex, it makes it harder to do things like develop the model, to calibrate the parameters that you aren't able to measure directly, to implement the model, to program it in the computer and test it. It's harder to communicate the model, to write down exactly what it does and therefore to publish it. And it takes a lot more work to understand how the model behaves and how you got the results that you did. And mainly, the problem with complex modeling is it's hard to stop building the model and start analyzing it and learning from it. And what that means is, it makes it that much harder to finish your PhD. So, this is something that we struggle with many of our students, is that they want to keep adding things to the model instead of saying, okay, that's enough. Stop, learn from the model, publish something, and graduate. So this just raises the question, how complex should the model be? How do we decide the right level of complexity? So if even an individual-based model can be too simple, so it's not useful and it's boring, you don't really learn more than you put into the model. But if it's too complex, the model's hard to build and use and believe, and you don't finish your PhD. So the primary factor in choosing a model's complexity, I think most people understand this intuitively, is to have a clear statement of the problem that the model is trying to address. So a model should only contain what is necessary to address a particular problem. So if you don't need some things, some processes, some assumptions to solve a particular problem, then it shouldn't be in the model, and you should force yourself to leave that out of the model. And if your model doesn't have a clear and sharply defined purpose, then you should stop everything you're doing and define a very clear purpose of the model. So at this point, I want to show my first example model. It has to do with salmon in the Sacramento River in California. This is very interesting because I don't know if I've ever given a presentation to a room full of people that might not be familiar with salmon, because they're the most important group of fish and probably the most important group of animals in California, where I live. These are fish that live in the ocean until they're adults, and then to reproduce, they swim back up into rivers and small streams where they spawn, they mate, and produce eggs, and those eggs live in these small streams. And then when the little fish are born, they live in the small streams for a few weeks or a few months, and then they migrate back down to the ocean. So this was a project that I started working on about 10 years ago, maybe more, 12 years ago, where the objective of the model, I basically was asked to help finish a project where the objective was to develop a management model for these Chinook salmon, is the species in the Sacramento River in California. So I want to briefly describe the life cycle of these fish. It's very complicated. The first life stage are the eggs, which are placed in small streams and rivers. The eggs incubate for several months. And the scale for modeling is very small. These eggs don't move. The environment affects them only over a few centimeters. So if you're modeling that process, you would need a very fine-scaled model. And then when the juveniles are born, they swim around and feed in streams and gradually move into larger rivers and migrate down to the ocean. And so the spatial scales that processes related to the juveniles, they happen over a few meters. That's the distance over which they feed. But then the amount of space that you have to model is all the way from these small streams where they're born all the way down to the ocean. And then when